Hello everyone. So today I just wanted to show you a graphical representation of how the original function relates to its first derivative and its second derivative. And for those of you who haven't seen this before, this particular website is called desmos.com. It's a really wonderful tool for students to be able to use and access for free. It's just an online graphing calculator. I highly recommend going onto the internet, using this graphing calculator to be able to create different visuals of things that you're working on at home. So first I wanted to put the original function up here on the graph. So as you can see, we have 1/3 x cubed minus 1/2 x squared minus 2x plus 1. So as we've talked about before with the first derivative, what we're really trying to find is where your original function has a maximum or it has a local minimum. And it will also tell you the direction of which your graph is going. So here, when we're going and increasing, that is where we'll see the first derivative being positive, and then between the maximum and the minimum, where your graph is decreasing or you're going downhill, that's where we're going to see a negative, and then it should switch back to positive. So let's add the first derivative on top of this graph. And the first derivative you can see is x squared minus x minus 2. And so again, as I just said, where we're looking to identify this local maximum and this local minimum, what you'll see on your first derivative is that's where your graph crosses the x-axis. That's where you change from your function being an increasing function to where it's going to be a decreasing function. So you can see here all the numbers are positive, indicating your original graph was increasing. Once we get to this point, that tells you where it's going to switch from increasing to decreasing. And so everything in between here and here, so this line and this line, your graph is going to be decreasing. So that gives you a good idea of what you can expect to see in relation with the first derivative to the original function. Now let's go ahead and take a look at the second derivative. So the second derivative, as we mentioned, is really to look at where your inflection point is. So here your graph is concave down. That means that water would spill out of it if you poured it on top of it. Here your graph is concave up, meaning that it would hold water. So what we expect the first or second derivative to show us is what this inflection point is where it changes concavity. So the second derivative is 2x minus 1. If we click on that, you can see right here that just as we expected, where the second derivative crosses that x-axis, that's where we're going to get our inflection point. The other thing that I wanted to point out is that, as I mentioned, this is where it's concave down. And so here your second derivative is going to be negative to indicate that it's concave down, negative down. And then it switches to being positive, which is why we call that our point of inflection. Now the other thing that I wanted to mention just in this brief example is if we were to take away the original function, I wanted to just point out how the first derivative and the second derivative relate. So in this case, the second derivative is the derivative of the first derivative. So you can see that in this case, here's our first derivative, and it has one local minimum. So what we're expecting to see with our second derivative is where it crosses the x-axis is going to be the same location as what the minimum is. Indeed, you can see it follows the same pattern. So here's where it's negative. That is where your first derivative is going to be decreasing, and then it'll switch to increasing, which is where your second derivative starts to be positive. So I just wanted to give you this quick overlay of how the original function interacts with its two derivatives so that you can see how to interpret each of the graphs as you go.